I'm going to leave. That's not a signal that this is boring and not worth it. It's just, hey, I have a friend leaving tomorrow morning, so I want to say bye to him. But with that, we'll hand it back over to the one and only Colin Nielsen, because he really knows what the fuck he's talking about.
My best. Right. Could someone talk about recursive circuits, right? Could someone sanity check me and just check the YouTube stream link in the meetup description to make sure that we're going, because I've been halfway through one of these and it wasn't ready. It wasn't live, so that sucks. Oh, yep. I think we're live. We're definitely live. Cool. All right. Let me pull up the meetup here. Okay. So today, today's topic is bit operations and cryptography. So this topic kind of spun out of some recent work that I've been doing in Noir, actually, to do some like manipulation against integers and turn arrays of 64-bit integers into arrays of 8-bit integers and kind of all that nonsense, that low-level nonsense. So one, I got into this kind of recently, and two, I was just thinking like. I went to a coding boot camp, was doing a lot of like high-level JavaScript stuff, and I'm gonna swivel here. I don't want to sleep in the crowd. I've never done this before. You guys make me all like sweaty and nervous. The chair's broken. And so I didn't know any of this stuff until I joined crypto. So I didn't know anything really about cryptography. I didn't know anything about bits and bytes. Until I got into crypto. So the goal is to maybe start from like first principles, because I've alluded to it quite a few times in some of these deep dives that Solidity is not so scary when you understand Ethereum as this 32-byte stack machine, right? Where it's just like processing and interpreting bytes. And when you can process and interpret bytes side by side with Solidity, things become much easier to understand, less black boxed, and you just like kind of understand how the blockchain is processing your transactions. With that too, like once we start to build these foundations of like, what is a bit? What is a byte? How do they relate? All these puzzle pieces start fitting together about cryptography. And yeah, it's, you just end up learning a ton about the environment that you're writing in. And I think about computer science in general. So to me, this is super interesting stuff. And I'm willing to go like as deeply or as quickly through some of this stuff as possible. So I think like, I'd love to get like a temp check from the room, right? Like we could say like simplest left to right is like, we go from like bits, and sort of like why the EVM is designed the way it is, bits, bytes, EVM design. Then we go to like some bit operations, so we get a little more comfortable with them. And then we can like move into cryptography they sort of build on each other. But I want to see like who's more interested in what, like where do we feel like the gaps in our own knowledge kind of reside. And then maybe we can all spend some more time there. So if you're more interested in going over like bits and bytes and integers and how all that works, let's do like show of hands. Okay,
what's the second option again?
And the second option is more like underlying cryptography. So like elliptic curves and like ECDSA and just some primer stuff. So I won't be doing elliptic curve math because I don't know how, but I do know like I have like a poor man, like a working man's understanding. I have a blue collar understanding of like of how elliptic curves work, just so that we can like kind of hack some stuff together and have a mental model for what can and can't be done, so we can build cool stuff, right? That's kind of the goal, is like that working knowledge. And so that's option 2. So let's do show of hands for that. Cool. So honestly, pretty split throughout the room. So I think we'll probably just spend equal time on both. I just wanted to make sure that like no one thought that like bits and bytes were super boring. So good. Okay. So let's see if we can find. Was there a dry erase marker anywhere here? I think I actually might get up on the whiteboard, because some of this stuff is good as sort of
This
whiteboard.
one right here. The marker. I think you're asking for the
eraser. Yeah. Does anyone have a dry erase? Does anyone have like a trusty backpack dry erase marker?
Maybe you could ask outside.
Yeah, I bet there's one in the building.
Oh yeah, sure there is. No, those are just pens. Those are just pens. Shoot, I'm prepared. That was a think tank. Yep. All right, found something. All right, cool. Let's see. Webcam. Yeah. So let's see. To get started here, let's just go over bits and bytes and some of the definitions. Are we all comfortable like with the concept of a bit? What a bit is? Bit is like the smallest metric, like the smallest unit of computing. It's just simply a 0 or a 1. It's an on or an off value. It's a Boolean, right? It's true or false. So that's it. That's a bit. It's the simplest, most granular value that like a computer can use to build programs, right? And then building on top of that are like, who can tell me the definition of a byte? 8 bits. Yeah. So it's how we represent 8 units of bits. So yeah, I don't know. I haven't taught this before, but with a whiteboard. But yeah, so there's 1, 2, 3, 4, 5, 6, 7, 8. That's 8. That's 8 bits. And so how we can represent 8 bits most commonly, we can represent. So here we have 8 bits. 8. All right, here. Sorry, I didn't think about this. Okay, so one bit has two options, right? It has a 0 or a 1, right? 1 byte is comprised of 8 bits. So how many values could fit into 1 byte? 16. Does that click for everyone? Like that compute, right? So if you have 1 byte can be 16 bits. So, and a bit has like 2 options. It's either a 0 or a 1. So you just multiply the 2, and then you get 16 out. So like we can store 16 different types of values in 1 byte. Kind of like in the same way that we can store in one register or one place value of kind of like the normal base 10 system that we use. We can store 0 through 9 in one place. In the same way, you can think about we could store 0 through 16 in 1 byte. But the problem is like, well, how do what's a nice way to represent a value from 0 to 16 in one place setting. And so that is where we use hex. It's where we use hexadecimal numbers. So hexadecimal numbers is it says like, okay, well we want to keep these things in one place when we represent them. And we only have like 0, but we only have like 0 through 9 as numbers in a base 10 system. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we go A, B, C, D, E, F, right? And so that gives us 16. And so that's like, that's the basis, bytes, it's the basis for how data is transmitted and really represented. When we stream bytes between computers, between protocols, any kind of messaging is really represented as bytes itself. And I think it's kind of cool and kind of nerdy that like actually that every single oh, Wireshark, every single like messaging protocol, this is how this is just totally sorry, 1 second, I'm trying to remember how to use. You don't have permission. Oh shoot, this is on an old interface. But I just want to say, like, we could find a screenshot. The way that computers send messages back and forth to each other is by streaming bytes back and forth. So you could just arbitrarily send bytes to another computer, and the way that those bytes are interpreted and serialized is depending on like what's called like a messaging protocol. So if you've heard like TCP, UDP, HTTPS, these are all protocols for that define how computers are to communicate with one another. So what I wanted to show you guys is like this is how your computer is processing in and out incoming streams, and it's sending outgoing streams of data all the time, right? So we have source IP, destination IP, and then here's the actual bytes in the stream. So it's 0, 0, 0, 0, 9, 5B, 2D, 7C, and so like your computer can stream bytes to any other device in the network, and they all go through this destination port 80, and this is all defined kind of based on a spec. So all that to say is that like this is when we talk about bytes and Ethereum, this is nothing new. Byte streaming is intrinsic to how computers communicate with each other. Different systems communicate with each other. And so, we use these bytes most commonly kind of as a representation for any kind of arbitrary data. How we represent that something is hexadecimal, because there is the case where something could just be like 0, 1, 2, 3, 4, and these are actually all hexadecimal slots, but the values are just really low. So what we tend to do normally is we tend to prepend a byte stream with 0x, and that's where we get 0xcoolguy.eth, right? Like this is the meme of Ethereum, right? Is these things start with 0x, it represents hexadecimal values, and yeah, that is how that works. Any thoughts? Any initial questions? Just wanted to set the foundation, set the stage. Yeah, go ahead.
How many bytes are in a hexadecimal?
Yeah, how many bytes? So
2 hex to 1 byte, right? Because the hex is 4 digits.
So there's what's called a hex. You'll see it represented as like a hex nibble most commonly, which is just because it's a little bit more than a byte, but it's just two bytes next to each other, right? So
Oh, okay.
Yeah, so you'd represent it. We'll start to see it because we'll start messing around in Chisel, but it's represented as like 0x to represent that we're doing some sort of like byte interpretation, and then like FA or something like this, right? And so that would be 1 byte of data, right? So when you see a 32 byte value in Ethereum, you'll see 64 characters, because this is 1 byte, and then you multiply that by 32. In Ethereum, your Ethereum addresses are 20 bytes long, and so if you've ever noticed, your Ethereum address is times it's x2, so you have 40, and then you stick a 0x on the front, so your Ethereum address is 42 characters long in all cases, but it's a 20 byte value. So yeah, we represent these hex values as characters, and they come in pairs, so they're little nibbles, hex nibbles. Yeah. Any other thoughts? Cool. Yeah. So let's talk about bits in the context of Ethereum. So I would really recommend that you all open this up as well, but I will put the first link into the meetup comments. Oh yeah, I should keep the YouTube open just to see if there's any comments. Byte and bytes the same. Yeah, so a byte just means one. It's just a single value, so it's one byte, and bytes are just multiple. It's singular and plural. So yeah, they're the same. It's the same amount of data, but bytes is just like more than one. So there's a really great tool by the Foundry team called Chisel, and I can't sign in, I can't chat, but the meetup link is, oh shoot, is the people on YouTube. Sign in, I can't chat. So I'm going to use this tool called Chisel just so we can have like a little like playground and see like visual representations of this stuff. So Chisel is this cool little command line tool that allows you to run a Solidity environment in your IDE. So like all you have to do is you have to just hit Chisel, and then it opens up a prompt, and I can start to write Solidity here. Yeah. So I could say you went to 56, test equals 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I could hit test, and then I'll see, I'll blow this up for you guys. How's the zoom level? I'm trying to zoom this in more. Appearance.
I can see it fine.
Okay. Font size, 32. 32. Here we go. Wow, that did not work. What did I have, 23? 25? Yeah, it's better. Wow. Yeah, don't mess with, anyway. Okay, sorry, it's about as big as I can make it for some reason. But yeah, so Chisel gives me, it's a REPL for Solidity. And what's really nice about Solidity is we can use these big numbers. when just to give a little brief, when we see these things like uint 256, can someone tell me like what the definition of that means, and why do we signify that? Like what does that mean? A uint 256.
It's an unsigned integer, which means that I was gonna mix up. It means it can't be a negative value.
Correct. Yeah.
And then 256 bits is the allocation for size and memory, I believe. For that.
Yes.
Yeah.
Correct. So, to break it down one by one, unsigned means there's no sign at the beginning, which means it's not negative, so everything's above 0. Integer, that means it is a whole number, so there's no way to represent decimal values. 256, the amount of memory that number can take up. Ideally, like what I am trying to help you guys see through kind of some of these chisel exercises we're going to do here is I want you to start to see how Solidity and the EVM manages memory in terms of like I want you to see it as like the width of 32 byte values. So here we go. Okay, so first of all, if you're in Chisel and you run Chisel and you just type !H for help, you'll see a list of all the commands. So really like kind of what this does behind the scenes, if we run SO, we see that behind the scenes. So this is like a REPL here. And it's just going to put anything that you define into this run function, right? So if I say, uint256, again, test equals 1, and then I log SO again, I see that it's really just kind of putting my runtime values in this contract wrapper. So if anything's not making sense, you can just trust that this is what it's doing for you in order to kind of make this happen. So let's start to imagine how these values work. So I have this function out here, which is just a utility function that takes in any kind of bytes 32 value and just pretty prints it so that we see the full width, right? So like, for example, if I logged test, I see the decimal 1, right? And luckily, I also see its hexadecimal representation too, which will get useful as we go on, because we notice that like we could either represent numbers as base 10 or base 16, kind of in the 0x format. So if I say out real quick, this is just a pretty print it. But has anyone here heard of like overflow? Can anyone give like a quick explanation if they know?
You're talking about when you like, if you have like a u int 8, and then you do some number that is past the upper limit, it goes back to 0 or the 0.
Correct.
And
Correct.
starts over again.
Yeah. So computers only have so much memory to hold values inside of them, right? And so back to our quick whiteboard example here of this single, and for the stream, I'll switch back here. But for this single byte value, right? When you have a byte here, like say it's like 0x 0.1, and then as you increment up 0.2, 0.3, 0.4, 0.5, right? You get all the way up to 0f, and what do you need to do? You need to carry the 1 in the same way you do with a base 10 system, right? I get to 9 in a base 10 system, and then I run out of space. So what do? Is I carry the 1 and I add a 0. Our version of adding a 1 and carrying adding a 1 and moving the place over and carrying the 0 right in hexadecimal is going to be really similar, right? So once we get to f, once we run out of room, kind of in this first after we get to 16, basically, in order to represent 16 as a hexadecimal, I have to say, 0x1 0. So I go to 10, and so 0x10 is equal to what you and I think of as 16, because it has to flip over in the same way. And so when I run out of space, I would keep counting up. Right? So if I ran out of like in the same way that if I ran out of this first place at 9, I'd run out of space again at 99. With a full byte, if I ran out in the first place at F, I would run out again at FF. So 0xFF, that's the maximum amount of space that I can contain. And this value, we'll see what that value is, but does anyone have any guesses as to what that magic number is?
120.
Close. Oh, wait. Say it again.
I think it's 2 to the 8. I think it's 128.
Close. Anyone else have it?
256.
Closer. It's gonna be 2. It's gonna be, so if we just in our REPL here, if we just did 0xFF, 255.
Oh, 'cause 0.
Because 0 is a valid number. So we get 256 possible numbers in 1 byte, right? And so
You mean in one hexadecimal?
in 1 byte, which is
2 hex.
which is
8
one.
bits.
No. It's two characters. So it seems misleading here. This is 1 byte. It's 2 characters wide, right? When we represent it as hexadecimal. But like one byte is it can represent the numbers 0 to 255. So
Oh, I see.
it has that much space,
I
right?
got you.
And so if you ever needed to represent a number that was bigger than 255 within your program, you would need to use more byte space. Shoot, give me 1 second. I'm sorry, someone's watching my little brother and they're calling me.
This stuff always confuses the shit out of me.
Yeah.
Yeah, I guess the best way to think about it is you just have a value. A byte is just a value of 0 to 255, and then there's multiple ways to encode it. Just think of it as encoding.
Yeah.
And like the hexadecimal is just, you have 2 pairs of hexadecimal numbers, so that's 16 times 16 is 256. So that's like just a different way to encode it. There's a bunch of other ways to encode them too, represent them, like base 64 is pretty popular. So base 64, you're only taking like, you have 64 possible values. It's like, capital A, big A and stuff. Like Bitcoin has their own version called like base 58, right? That like removed a few characters from base 64, and like they're all just ways of taking numbers and then representing them in like more compactly than just 0, 0, 0, 1, 1, 0, 0, Yeah.
Does it
Yeah.
UTF work the same way?
UTF-8 is variable length encoding, in the sense that like it'll start out like ASCII, but then like you have its value 0 to 127, and if it's greater than that, then it'll start using like more bytes. It could have up to like 4 bytes for one
Gotcha.
character.
So it's not, this is more optimization than UTF-8 is just to accomplish.
Well, this is kind of just a way for our best humans to look at like bytes in like a more readable format for us. Whereas UTF-8 is more like, I think of it more as like a protocol. Like if I wanted to write this weird Sanskrit character, how would I like represent that as bytes and tell somebody else about it?
Yeah.
So like they're kind of like opposite. They're kind of like the 2 opposite sort of things.
I think your stream might have the webcam on still. I'm not sure.
Yeah, interesting.
Yeah, it's on the webcam view.
Maybe.
No, I don't think. I think whatever. Oh wait. No, it's we're good. Yeah. So the convention here is that when we refer to them as bytes, we obviously use bytes. We use bytes 1, bytes 2, bytes 3, bytes 4, bytes 32, right? But when we use integers, we talk about integers in terms of bits. So the key term here is that like say we have a bytes a byte's 30, we have 32 bytes worth of width to play with here. How much space, what kind of uint could we use? What kind of flavor? How much width would we need? How much space? If this is 32 bytes, and uints are represented more so as bits, what would your guess be if we use uint 8, uint 16, different things like that?
32 times 8?
Yeah, exactly. 32 times 8, which is a uint 256. And so a uint 256 means that is an integer that's an integer that has up to 32 bytes worth of space, which is an incredibly large number. It's like more atoms in the known universe. It's unbelievably large. 2 to the 256 is very, very big. Most computers, I believe, use the 64-bit architecture. And so this is why I'm using Chisel, because it's a really niche virtual machine, because most computers run on a 64-bit architecture, whereas the EVM runs on a 256-bit, I wouldn't say architecture, but it works only with 32-byte, 256-bit values. Yeah, so for example, if we had a uint 8, which is saying that we have, hey, here's an unsigned integer with up to 8 bits of storage. If we try to put in 256, we get an error. Not allowed. And that's because it overflows, right? So if we said 255, it would say great. Let's do probably a more verbose test. So if we said,
it used to go to 0, right? Didn't it used to do, if it went over, it would just go to 0 and start over, but now it has the error.
correct.
Yeah. Locks on it.
Correct. So that's called checked versus unchecked math, and that's a big feature of Solidity version 8 and above. Is that before Solidity version 8, numbers would just overflow, and I'll show you what overflow looks like here, right? So if we have uint 8 num, and we set that to 255, and then so here's num, right, in memory, 255, and then if I said num, plus equals 1, I get an arithmetic overflow error, right? But if you've ever seen this cheeky keyword, unchecked, if you've ever seen that in Solidity, oh no.
You're not allowed to do unchecks.
Yeah, forbidden code. Okay, yeah. So if I used help. Okay. So if I used the unchecked keyword, and I said, num plus equals 1, close brackets, failed to parse input unchecked, num plus equals 1. Maybe it's a syntax error thing.
Is it not defined in that
Yeah, you have to
context?
redefine.
Num? No, num's here. So? Yeah, that is super weird.
Could you store it?
Num equals num plus 1.
Well, you would have to change the variable name, right?
Yeah, you gotta overwrite it.
No, it's a UTF. Just define a UTF-8 string. So I don't know what's going on there. So if I just said, maybe I'll just define a function real quick. So if I just said function test, public pure, because we're writing Solidity, and I said uint 8 test again equals 255. We could define that as a constant. And then if I said, I opened up this unchecked block here, and I said test again, plus equals 1, and then closed that block, and then closed this block. Oh, okay. Returns uint 8, and then if I then return out, oh, come on, if I return test again, failed to parse input. I mean, I know my code's ugly, but just let me do it, man. Maybe I am solidity unchecked. Give me 1 sec, sorry. Unchecked math. Here's the example.
Return it out of the unchecked?
No, you can. Theoretically, it could just be. I don't think it's a block scope thing. This is super weird. I'm bummed. Yeah, so. What? Anyway, oh, it's num. There we go. So num. I mean, I could have sworn I could do that. Not sure what's going on with our REPL here. So sorry about that. But it just turns off the overflow safety. So like, if you could just imagine, right? Like we have 0xFF. We have a fully filled byte. If we add 1, we would do the same thing as we normally do, right? We set all these to 0, and then we increment, we add 1 and then add 2 zeros here, right? But if our width is only, if we can only fit 1 byte worth of width, remember 8 bits is 1 byte, so uint 8 only has 1 bit, 1 byte of like resolution, right? Like what would happen is like these would go to 0, right? And then you would get like 100 as a hexadecimal. But since it only has like 1 bit, it truncates that, right? So basically it flips over. So it goes back to 0. It's like on a clock. If you're familiar with like modular math, right? It's kind of on. It's like this. It's like the same effect. And so we normally like kind of scale up and down. We use these different bytes values, but the purpose is that Solidity runs on these 32 byte values, right? So I guess first of all, before we move on, any questions about that? Like, is this kind of coming together here?
I have a question, and if it's not super relevant, then we can move on. But as
Yeah.
far as like memory packing, does that mean that like it's not always going to take up 256
Bless you.
bits? Like when you define that as a uint 256, is it always going to take up that much, allocate that much space even if it doesn't need it?
Correct.
Okay. It
will. So if you use the uint 256 tag, it will never pack down in storage. And it's I guess you could call it like a scalar value or a literal type. So it will store it on the stack, and it won't store it in memory, right? So let's see if I clear this, and if I start with like a fresh REPL here, and I say uint 256, so I define a full width 256 uint, and I say a equals 1, and then you can use this command here called SD, which stands for stack dump. I can see at the top of my call stack is the value 1. Really, this is whoa. This is kind of a bad representation of the stack, unfortunately. Raw stack, let's try that. RSA. Yes, this is what it looks. This is literally what the call stack will look like in Solidity, because the call stack is it's like an array, right? It's a stack array of commands, and they're measured they're like 32 bytes wide, right? So they're always going to have the same width, regardless of the value that you set them at, right? So as you can see, we have like this 32 bytes wide. So we define this as a UN256, and then so when I look at the stack reference for A, I see that like at the top of my stack is this value, and really all these values are 32 bytes in width. And just to like prove the point, if I do a new variable called which is a uint8, and I call it B, and I put in 255 or something like that, like we had before. If I then do another stack dump, see there's B at the top of the stack represented in hexadecimal. It's a one full bit, right? If I how it literally looks in the stack. So if I did a raw stack read of B, it still has the same width. So yeah, I don't know if that helps kind of answer your question. So the EVM will always use these 32-byte values in memory and in size, but it'll only pack in storage. And when you say that something is a uint8, what you're actually doing is you're adding range checks on the value itself. So you're telling the EVM, hey, if you see a value that is 256, right? So if we try to say like B plus equals 1, right? You're not literally telling the Ethereum computer to like store it as an 8-bit number, as a uint8. You're telling it, hey, this 32-byte value that you're going to store and manipulate should only have a width of 8 bits. So revert the operation if you encounter something here that is greater. It's a range check essentially. So it's like if it's if you try to go less than 0 or higher than 255, revert the operation. But it's still actually the way it works with it is a 32-byte value, which is why it's inefficient to try to pack things in memory, but efficient to pack them in storage. So you take all your variables in 32-byte kind of chunks, and then you only pack them and do range checks when you store them down, because it's more expensive to say, because you're adding a range check for every single value.
Oh, so memory. That's why everyone just uses like UN256 for memory.
Yep.
Like, oh.
Yeah, for memory.
I did not know that.
Yeah, and also like this is getting into some cool other Solidity stuff, which is I'm glad we're here, right? Because like there's a few different there's two different places. So there's the stack, and then there's the memory array. So just to be clear, the Ethereum virtual machine is a stack machine. So it processes these commands, right? So if we wanted to, we could spend I don't know, thoughts, 3-minute rabbit hole on stack and memory, if that's useful for people. Okay, cool. So there's three unique locations that the EVM has available to manipulate data and to process data. So the way it handles and computes instruction sets is in the stack. So we have a stack here. Then it also, if it needs it, has a memory array, which so the stack is 32 bytes wide. The stack is 32 bytes wide, and with a I want to be so brazen as to say n depth, but I think if we've developed Solidity, have hit a stack too deep error. So that's not true. I don't know what the actual depth is, but it has some theoretical maximum that you hit if you're doing anything more than trivial, and it's annoying. But there's also a memory array, and so that's a little bit of a different data structure. It is volatile in size, right? So it can be n length array, but it has this kind of Solidity uses a specific like rule set to interact with it, and depending on the language you use, the rule set might be different, and that's where things get kind of fun between languages, between EVM languages. So like Huff, Solidity, I think they have different ways of initializing memory. If you've seen some spicy Twitter memes from some Solidity devs about the free memory pointer or the 0 slot, that's where this comes from, and I'll show you that in a second.
Is Viper different too?
I think Viper is different, yeah. I think the free memory pointer and the way that the Solidity manages the memory array is unique. And then also there is a so this is so what I can do is I can push and pop, right? I can push and I can pop. I have all sorts of ways that I can interact with the call stack here. I can push, I can pop, I can swap, I can do a whole bunch of different stuff. And the memory array is like volatile, and then there's also a third spot. I'm kind of running out of space here, but it is it's call data. And so call data is simply, it's very similar to memory. So it's like kind of it takes in an array of data, and it is just the call data included with that Ethereum message. And I guess the important part is it's read only. So like if you've ever used reference types before in Solidity, and you notice that it's cheaper when you're using a string as a parameter to say that string is call data instead of memory, that's because when you pass something as a parameter, it's in call data anyway, and when you type it out as memory, you're asking Solidity to copy it from the call data into memory. So it adds some extra operations for you. But most importantly, call data is read only. So you can reference it, you can look up to it, and you can read slices of this array. So it's a read only array. But you cannot modify it. So it's just the place where all your transactions kind of bundle into. And so we've talked about this a little bit in other deep dives, but like Ethereum as like a really kind of naive but really secure messaging protocol is like when you create a new message on Ethereum, there's like a from address, a to address, and a data field. So like you have like the from address, which is like, my wallet or whatever, or this contract to another contract, is sending the message to, and then any kind of data you want to include, there's a data field here, and we'll see what that looks like. But that it's the same way as TCP, UDP, and HTTPS, where there's a header that says, hey, the first 4 bytes here is going to be the instruction set. It's going to be which function to call, and then the rest of the bytes are going to be just the parameters that you pass in. But this data here is call data. So when you see in your Ethereum transaction this data field, that's call data. So that's that special data location. And so, for example, and you can go and look at the proxy talk that I gave, the recordings on YouTube, that talks a little bit about that. So like, it's like, if I go back to the REPL here, if I do a stack dump, you probably noticed. So given the context here, right? Given this function run, which is called, it's the entry point for the REPL. Given the function run, and given this variable that I defined a and b, which is, this is going to be 1, this is going to be 0x, ff, right? If I log the whole stack, we notice that we have, this stack, which is like 0 to 3, right? And so it's like, well, first of all, like what is this value here? This is ridiculous. Like this is super random. And also like the 0x33, what is that? And so like what I said about you can use evm.codes as a reference. This has all the codes for the EVM, and these opcodes are hexadecimal values, and they're the instruction set for how Solidity is supposed to, for how Ethereum is supposed to modify data, interact with other contracts, create new contracts, etc. So you see like all the way from 00 to 0xFF, we have these special codes that are instruction sets. And so what we see here as the first value is kind of interesting. And what that is I'm just going to spoil it. If you remember from the proxy talk, it is the bytes 4 of the Kichak 256 hash of the string of the function signature. So it's the first instruction set that the EVM receives is, hey, call this function that has the tagline run. And so it's calling run. And then 0x33, the decimal the decimal value there is 51. So if we would it be 33 or would it be? Oh yeah, no, this is hex. Okay. I don't know why. It might be loading the color. It might be the initializing the memory. But either way, so yeah. So the first thing it does is it calls the run function, right? See, we also have this MD memory dump. So we can let's log what memory looks like. And so it's like, okay, this is where we start to see, it breaks it up into 32 byte chunks just so it's a little more readable, but technically it is a volatile memory array. And we can edit this with like mload, mstore, things like that. But Solidity has a way to manage the memory as such, whereas 0 to the first 32 bytes, so remember that 0x20 is just going to be 32 bytes as a decimal, right? So the first, so index 0 to 30 is going to be, these first two slots are reserved. This is called the 0 slot, and this is called, I think, scratch space. And then this is going to be what's called the free memory pointer. And so the free memory pointer, regardless of what happens during your total execution, regardless of what happens during your function, right? So if I was to define like a bunch of strings, like if I was just to pollute memory here, so if I was going to say like string memory hi equals like hello, this is a message, and I'm asking Solidity to store this in memory, and then I do another memory dump, you'll see that I'm like starting to add stuff into memory. And then if I do another memory dump, it just gets bigger and bigger and bigger. But notice this free memory pointer. So this is, it's always going to be the memory array at slot, at slot 60. Index 60 is going to have the value where memory, the next free memory slot is free, right? So notice this is 0, 40, 60. So you said the memory array is full up until index 80, right? So 80 is the next spot to use. That's where any kind of reference value I want to put in memory, I store starting at 80, and then I update the free memory pointer. And this is what Solidity is doing behind the scenes, right? So like we see this here, right? So we see when I add this string in there, then the free memory pointer becomes C0, right? And when I store this another string in here, the free memory pointer becomes 100. here's another cool like caveat. If I go to any smart contract on Etherscan, that was compiled using Solidity, right? So like here is here's a transaction to a smart contract, right? If I go to, oh yeah, this is to Seaport, right? If I look at, oh yeah, if I scroll, oh man, Seaport. If I scroll all the way down and look at, oh, Seaport is actually the worst example because it's all written by hand. Let me find something that's like not custom. To this is contract Tether, perfect. Tether was written in real Solidity, not written by hand. So here is the contract.
When you say written by hand, do you mean like they wrote the opcodes themselves?
Yeah, Seaport is insane. It's written in Yule. Yeah, it's nuts. So like, yeah, so for example, here's a normal contract. All right, here we go. So let's look at the first two lines of the bytecode of any smart contract written in Solidity. You'll see 060, 080. So the first thing, so like these are instructions to EVM.code, like to the EVM. So if we look at 60, push 1, which pushes a new value on top of the stack. So it pushes, so it will push a value onto the stack, and that value is going to be the next variable 80. And so it's going to push 80 onto the stack. So what it's going to do is it's going to push 80 onto the stack. So those are the first two bytecodes. And then it's going to push another opcode 40 onto the stack. And 0x80 and 0x40, push 08, push 40. Block hash, that's not right. It's super strange. I think I'm missing something here. I'm definitely missing something. But
I'll go back.
Which one are you looking for?
I'm looking
It
for.
says switch to opcodes view. Is that anything?
Yeah. Okay. Thank you. Thanks so much. Okay. Yeah. Whew. So it pushes the value. Yeah. Okay. Oh, right. Because it's a value. It's not an opcode. So it pushes the hex value of 80, and it pushes the value of hex code 40, and then it calls the mstore command. So mstore takes two arguments off the stack, the offset and the value. So it's saying, hey, the offset is 40 and the value is 80. So what this does at the beginning of every single smart contract call initializes the free memory pointer. So it sets, like you can watch it kind of set up its memory. So it, and that's just how Solidity does. So like the first instruction set in every Solidity smart contract is initialize the memory pointer here. And then this memory pointer gets incremented and decremented throughout the execution of the contract. A little longer than 3 minutes. Sorry about that, but but yeah. So I guess does that kind of make sense that like when that like Ethereum is a 32 byte stack machine, right? And when I say bytes 32, like when I am writing numbers, and I'm just doing this for formatting, but like when I'm writing numbers in Solidity, really they're being stored onto the stack as 32 byte hexadecimals. And even if I say that something's a UN8, it includes like a range check. It just includes a range check to make sure that this number is in fact smaller than the maximum width that I can handle, right? So you can start to see here that these are just like massive numbers that fit into 32 bytes. And then boom. So I've I've now officially gone over. So there's a pretty full number. And if I wanted to see what the full number is, Solidity has a special type wrapper where I could say type un256.max, and that is the maximum number. And you see there's the hexadecimal representation of just like a full 32 byte slot, and then there's the number integer representation.
So you could like packing with structs, right? Is that like the main way that you would
Yeah,
pack them bytes?
in memory and in storage.
Can we do an example of that?
Yeah, so let's look at that real quick. So if we said struct my struct, and then if we said like uint 8 first, oh no, yeah, is this right? And then uint maybe 160 second, and then address edr, and then we could also say like maybe put like a uint 16 in here, or maybe a uint 32, sneaky 32, and then I have this struct definition here. Just make sure, yeah, so there's my struct, it's defined there. And so if I were to say, actually what I'm going to do is I'm going to clear the memory here. I'm going to redefine the struct, and then I'm going to say my struct A, well, I'm going to define a memory location, A equals my struct, and then we're going to say first is going to be 255, and then sneaky 32 we'll just say is 10, and then we'll say address is, well, we'll just ask it to, we'll say that this is our uint 160, and then I'll grab my address as a secondary. And so if I log A, I see, I guess it shows me that the tuple, which is interesting, but I think what we really want to get at is we want to do a mem dump, md, yeah, interesting. So that's not what I expected. So let's look at this. So it says the free memory pointer begins after index 100, which is correct, right? And then looks like our values exist here. So maybe maybe that only works.
Surpass the amount of space per block in those in that struct.
No, I didn't. So I think. So let's look at the RSA. So interestingly enough, when we do a stack, it will tell us the memory location, the memory pointer. So it's at 0x80, right? So the memory pointer. So it starts here. So I think it packs.
Were you expecting it to all be in one memory address there instead of 4?
Yeah. I was expecting it to, right? So here's our address. Here's our big number. Here's the number 10, right? Yeah. So if we said 0x0a, that's 10, and then if we said 0xff, it's 255. So I'm not sure. So I could see two things happening here. One, maybe it only packs structs and call data. So like if you defined a function test that took in my struct and referenced it as call data, and then said A, and then maybe I don't know if can we console on in here. Visibility public, public, what do we want to put in here? Maybe we could. I don't know how we could log this. Maybe like VM cheat code reference. Let's see in the files logging environment log. Nope. I think there's a console log somewhere in here. Utilities? Nope. External? Nope. Nope, 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 nope. I'm not sure. Yeah, maybe we console logging. I don't know. Maybe we could just say
It's like
console.log.
console log int, log unit, log string.
Well, I want to log the whole struct, or I at least want to log the in representation of memory. So maybe I could say like console.log bytes, and then say ABI.encode A, and then maybe I could return that out and remember to do a. Yeah, console's undeclared. So, shoot, maybe I can just do that and then say
Oh, it's in the standard library.
memory and then say test1 and then call test1. Oh yeah, and then we pass SO. Maybe. This is very sweet.
I wonder
I don't know how to
does-
handle this.
Does memory not do struct backing, maybe?
Perhaps. This is probably a good question for the Solidity docs. So yeah, I think this is maybe unexpected to me. Maybe it's possible that these are ABI encoded, not ABI encode packed. So, yeah. I think, well, that'll be some extracurricular research. Any other thoughts about that? Questions?
How do you make like, because I know everything's open source, but I'm sure some companies have like kind of a closed end kind of thing, so like you don't steal their IP,
Mm-hmm.
like
Intellectual property.
yeah.
Mm-hmm. Yeah.
So how do you like publish something on chain, but like kind of
Mm.
obfuscate it a little bit, I guess?
Yeah, I mean that's the hard part. Theoretically, it's like that's the balance, right? You could deploy something on chain and not verify the smart contract. People can still decompile the bytecode, and
Oh, okay.
since the blockchain is deterministic, and the bytecode that you see on chain here,
Like on Etherscan.
yeah, on Etherscan, it is. I think we closed out Etherscan, but yeah, it is. That code will run every single time, right? It's deterministic, and you could like pipe that into some sort of software that does like an analysis on like how certain inputs would affect certain outputs. So like.
Oh, okay, so like a virtual machine that kind of just runs endless like tests on it?
You could pretty much, if you really wanted to, you could get it to a point where you understood exactly what was happening in the smart contract. Yeah,
I see.
because and that's how we want the Ethereum blockchain to work.
Well, yeah.
So you can make it tough by not verifying your contract, but yeah,
Okay.
yeah, that's kind of the nature of the beast. Yeah.
There's also like different, doesn't prevent people from copying up different like licenses for your, that you can like put into your smart contracts. It doesn't really do anything, but some people put different licenses. Like Uniswap has some stuff that's like,
Yeah.
they're protecting things, right?
is it business source license, which
Yeah.
allows it to be a product for a few years before it becomes open source.
Yeah.
Yeah.
But you can still copy.
The last thing I wanted just to mention is bit shifting, because this idea of bit shifting becomes really easy once. Oops. Oh, it's a literal. Why can I not convert 12 to a bytes 32? Because I have to first cast it to a UNT56. Okay. So, all right. 255. There we go. Okay, so I just wanted to talk really quickly about bit shifting, because bit shifting was always like super mysterious to me. But when you understand bytes and bits like this, and you think about it in terms of like hexadecimal and nibbles, right? Things start to make a lot more sense. So like, for example, it's the same as like concatenation of numbers, right? Of like, you know, it's the whole JavaScript problem, right? If you have the string of 1 and you add it to the number of 1, you get 11, right? Like, it's kind of the same. It's the difference between this. Basically, yeah, you could imagine like bit shifting, you know, bit shifting by bytes specifically, like by values that are divisible by 8. It's going to be the same as like kind of the string concatenation. So it's the difference in normal math between that and that. So like, you know, 1 plus 1 is normally 2. But with like bit shifting, we start to see this like concatenation kind of form. So like just to show that real quick, right? We have a couple different bitwise operators that are pretty common. And we have and, or, XOR, and not. And, you know, for me, I don't know if you guys feel this way, but it was always really scary to see these values like in the wild of like a single and. It would be like, ooh. Or like if you start to see like double carets, which is shift right. So like this, you know, this is shift right. This is shift left. This is bitwise and. This is bitwise or, right? Yeah, they were always kind of scary to me. So
Shifting was always like the most confusing thing to me.
yeah, it's like it was. Yeah, no, the actual shifting is super confusing to me as well. And so like, I think this will really kind of start to come together. So if it works left hand. The arrows are a little confusing, but it works like, you know, modify left side. Modify the right side against the left side with the operator, right? So it's like, it's shift this left 8 bits. So if we were to shift this left 8 bits, which is 1 byte, what do you think this value would look like in memory?
FF00.
Boom. FF00. We took this value here, and we shifted it right, 8 bytes. It's like, it all makes sense when you just like, it's like, oh yeah, look, you literally shift it right? And so like, as long as you're doing it in like divisible by 8, if you're starting to do stuff divisible by, if you're doing like, you know, if we shifted this right by 3, that looks super funky because we're doing a whole bunch of other stuff there. But like, if we're shifting right by bytes, then yeah, it's pretty easy, right? So like, if we shifted this right by 32, we would, I mean, what's, you know, 32 minus 8 is 24. 24 divided by 3 is, well, 24 divided by 8 is 3. So we should see 3 hex nibbles to the right-hand side. So we got 1, well, sorry, 3 in addition to. So we should, 32 divided by 8 is 4. So we should see 4 hex nibbles. So nibble 1, nibble 2, nibble 3, nibble 4. If we took this and then we shifted it right by 8, there are only 3 nibbles. Pretty easy.
if you shift the original one the other way by 8?
Aha, great question. So there's our original value. We shifted it right by 8.
Yeah, that overflow.
So it said the register was only this wide. Well, the register was only this wide, and then it shifted it right by 8, pushing the FF off the edge, and you lose it. So it's also like in the same way in which if you represent 0.9 or 0.1 as an integer, it will just return 0. Exact same thing. It just like rounds down, right? These bytes always round off. They always will go to the least common denominator. Yeah, so that's that. It'll just pop off the edge.
I'm
And
curious if you shifted by 32, it's just 0 still.
yeah, if we shifted it by, 256, yeah, well, if we shifted it by 7, let's see. Yeah, we should get something in there. Yeah, we get 1. We get 1 bit. We get 1 bit left. If we shifted it right by, it's not like it has a wraparound factor either, right? So 256, 264. It's not like it'll rubber band
It
twice.
just always backfills with zeros.
It always backfills with zeros, right? And the cool, and so like we could do all sorts of stuff, right? So like this is where we get and is like the flattening of values, right? So given this number, and given this number here, so let's say like bytes 32 A equals this, and then bytes 32 B equals that. So if we got A, we got B, right? So when we use double ands in like normal JavaScript or whatever, right? You say if left value and right value equate to true, then it requires both values to be truthy, and then it will return true. So we'll see how like and merges, and then there's or, right? So if we said A and B, we would get a 0 because there's no spot where in any of these FF and FF are aligned. There's no spot where there are truthy values in both places. But if we say or, see, it's kind of ugly because it truncates it for us. But so it says it doesn't matter the values here. It just kind of merges all the way down because it's like, hey, this is truthy, and this is truthy. Yeah, that's how that one works. Yeah, so there's and, there's or. I think that's there's XOR, which is exclusive or, and this is a great little table here, right? So like if there's 0 zeros, right? So if we took A, which is this, and let's do B instead. So if we took B, and if we said B and 0x, oh, that's super annoying. Okay, stand by. This is just a conversion thing. Okay, back to logging B. If we logged B, and if we said, so we have this value here, which has like the rightmost 6 bits, and we have this value here. And if we are asking for the place where only where these two both align and are truthy, we get these. We just get 0xFF. So only the right hand side was truthy. But if we did A by same thing, there we go. I just had to go farther out, right? So given A, which has a value all the way out here, and if we ANDed A with something that at least had this, it would only take the place where, it would only take the bytes that are, I guess, a line. Sorry, I'm kind of running out of steam here, so I'm not really explaining it well.
That makes sense.
But
I was just wondering, like, what do we do with this stuff?
Impress your friends.
Like, I see it in smart contracts.
right,
Every once in a while I'm like, wow, I figured out something to do with the bitwise stuff.
yeah,
I can never get to a point with this stuff where I'm like, I could see what I could build with this.
it totally, yeah.
It just seems dangerous to me.
It's totally dangerous, because it's nice to have safety around integers and just say like, hey, this thing's a uint8, right? You don't ever have to use it, but when you got to reach for it and to do some low-level stuff, I had to do that recently.
What were you doing?
I was writing a ZK circuit in Noir that tries to replicate the ECDSA recover function. And so what I had to do was, so this was my use case, right? So given a uint8 array that is 32 bytes long, right? So kind of these exact same values here, right? This is kind of like a byte array in a way. Given a byte array of 32 values each, combine that into an array of uint64 values that is 16 long, right? So this is type length. So we had, I guess the input of these two concatenated is going to be 64, thank you, 64 bytes total. And the output length is 1024 bytes total because 64 times 16 is 1024. So 1024 bits, 1024 divided by 8 is, so this was 128 bytes. And so what I had to do is I had to say, well, first I had to take the first value, right? So I had to say if there is, this one's a little goofier, but this one's a little, this one's more straightforward. Take a uint64 array that's 4 wide and transform it into a 32 byte, because this is the same in memory. So like 64 bits times 4 is 256. And 8 bits times 32 is 256 bits. But it's just changing the representation in memory. So I had to figure out the shift amount based on the iteration. So whether I'm shifting it 64 bits or not. And then I had to shift that value right a certain amount into the output index. And so this was like a low-level example where I had to transform the two. But yeah, I know we're at time, and I wish that I had more time to go into cryptography, because you start to see where this stuff is comes into play. But I guess for those who have 5 more minutes and want to see it, maybe raise their hand. If not, I'm getting kind of year in. Some people are down. Okay, cool. Well, it's been awesome. Thank you guys for coming out. We'll flip on the lights, and then I'll chill here and go through the last few minutes of this. So feel free to leave. Please grab some pizza on your way out. We've got a bunch of pizza left. So grab a couple slices of pizza, maybe a road soda, and don't do that. And thanks for coming through.
Thank you, man.
Yeah, absolutely. Thank you. Actually, I did want to get some quick feedback before people left about like the meetup itself. This is like number 8 that we've done. and there are quite a few. Well, there are a few people who have come here consistently, and so just like wanted to put out the offer for if you have any different ideas for how we could structure this to make it more engaging or offer more value for people, that'd be cool. Or if you even want to like teach one or do like a repo dive, I'm super happy to swap out too for a session. So just putting that out there. If anyone had any thoughts, speak them now or come to me in private.
Yeah, it sounds awesome. And I don't have anything now, but like some point in the future, it'd be cool to say a little something or go over something. So
Yeah,
I'd be down.
sweet. Dude, that'd be awesome.
Yeah.
I love that. Cool.
I guess I have one more feedback thing. Just like
Yeah.
some of the stuff, like the cryptography stuff. Like, how did you like learn a lot of it? Was it through a class? Was it just through your own research, or was there like a specific resource?
Yeah, through research mostly.
Okay.
Man, kind of bummed at the pace of this. Sorry, a lot of this stuff ended up was actually supposed to be on the SEP K256 curve, because that's what Ethereum is based on. So the whole reason why we have these 32-byte values is so that we can fit 32-byte private keys that run on this curve and do these Kachak functions, these hashing functions, and then also like elliptic curve math and verification more efficiently. And I found out about a lot of this stuff through like, I would say mostly YouTube videos. So this Ethereum engineering group, I cannot recommend enough. Imagine like, this guy, Peter Robinson out of Australia. And like, imagine if I was like way smarter, more concise, and had a cool accent and did this every single week. That's what he does. And so like, this engineering group is awesome, and I would really recommend it. And all their videos are on YouTube. They've been going at it for like 4 years. And so they have cryptography, security, engineering basics, and it's all kind of applied. So this one was on BLS signatures because I'm trying to learn like Schnorr signatures and BLS stuff to see if I can build something like an interesting like threshold multisig kind of project. So kind of a lot of it comes from like tinkering around. But yeah, a lot of videos. I have if you go to my YouTube channel that's linked here, I have this playlist on here called dude, what the heck? Where is it? It's called Soul Pro. There it is, Soul Pro. Yeah. So I learned pretty much, I'm just such a visual learner and I can't like read stuff, but like this was like a playlist that I put together called Soul Pro, which is just like all these Solidity chads that I found who are really good at this stuff. And so I threw a bunch of stuff in here. I need to get back into that, but yeah, YouTube is the answer.
Awesome.
Yeah. Cute. Sweet, thanks guys.
Thank you. It'd be kind of cool just to watch one of these videos, just talk about it
Honestly,
as
yeah,
like a group.
like a watch party.
Yeah.
I could be down.
Stream party.
Dude, Zeus, good to meet you, man.
Nice to meet you.
Yeah.
Thanks for watching.
Absolutely.
That's good.
Yeah, see you up in Boulder, man.
So for the account creation,
Yeah.
it's like a pseudo random number and like what runs it through a SHA-256 algorithm. How does it get that initial private key value?
Yeah.
You know,
So,
and that like stuff.
yeah. Yeah. So, there is, let me show you. So there is so how you get from seed phrase to ETH address, the whole flow of that?
Well, like, I'm actually thinking for the C phrase, right? Because the C phrase is like a representation of the quality of root layer B of the private key, right?
Mm-hmm.
I'm thinking like for the, like, what's actually generating the C phrase is that like pseudo-random number coming out of some kind of like.
I don't know how entropy works. I don't know how that entropy works. No. I've got no idea. Yeah.
No worries.
Yeah, yeah, I know. That's like your own. I can tell you everything after that.
Okay.
But
That's the stuff I'm messing with.
is the randomness?
Yeah, like the entropy generation on the really low level.
Shoot. Yeah, I unfortunately I don't know that one.
Yeah, no worries.
Dang, man. I wish.
Come up next month if you want
But it's like,
to
you have an application.
we'll watch it here as well.
I would love to. I'd love to. That'd be great to make my way up. I move out of Westminster like in 20 days. So got a few